Good morning, dear student. In today's lecture, we will discuss uh, the metallocene base alkene polymerization. So, in previous lecture, we already discussed the Ziegler-Natta catalyst for alkene polymerization. So, in this lecture, we are very much interested the metallocene base alkene polymerization. So, we are very much familiar with this metallocene. We know that that is this cyclopentadiene. If you consider a cyclopentadiene, then this hydrogen which is attached to the carbon, this hydrogen which is attached to the carbons are acidic, and by loss of one of the proton, this cyclopentadiene becomes aromatic in nature. So it is having a negative charge. These are the hydrogen. So this is your cyclopentadiene, and this is your cyclopentadienyl anion having a -1 charge. -1 charge. When this cyclopentadienyl anion react with two molecules of this cyclopentadienyl anion react with Fe, then it will forms the ferrocene. That is, two molecules of this cyclopentadienyl react with Fe plus 2, and then it will form the ferrocene. That is Fe. Okay, so this is your ferrocene. Sometime, so this is your ferrocene. Sometimes a metal ion with bigger charge is also forms the metallocenes. For example, if you consider the example, that is zirconium, it is in +4. Zirconium, it is in +4. It also form a metallocene, and it is known as zircocene. So this zircocene having +4 charge, and if you consider when it interact with this two cyclopentadienyl ligand, then to make a neutral molecule, it is also attached to two chlorine atom. So the overall complex must be a neutral complex. So if you consider the complex of this zirconium, then this zirconium, it is not same as this ferrocene. It is not same like ferrocene, because uh, to make a neutral molecule, so if you consider one of the eta 5 Cp, it is attached, again one of the eta 5 Cp, it is attached. So this zirconium, it is in +4 oxidation state, but this cyclopentadiene having -1 charge, so the charge is not balanced. To balance the charge, this zirconium is attached to two negatively charged chlorine atom, and therefore the overall oxidation state of this zirconium is +4, and this ligand contribute -4 charge, and therefore it is a neutral molecule. Therefore it is a neutral molecule. So if you consider what is the difference between this ferrocene and this zirconocene, if you consider uh, due to this chlorine atom which is attached to this zirconium, the zirconocene are little different from ferrocene because of the two chlorine ligands take some space, because the two chlorine ligands take some space. So to make the rooms for the chloride ion, the ring becomes tilted, the rings becomes tilted with respect to each other. So the rings become tilted, so the rings, these two rings are adjusted in such a way that the chlorines are it will available, it will provide the space for the chloride ion. So these rings are tilted, it is not same as ferrocene. So if you see the difference between this ferrocene and this is your zirconocene, so these cp rings are tilted in such a way that it will provide space for this chloride ion. So this is the difference, no doubt. This is also attached to 2 cp ring, this is also attached to 2 cp ring, but to make the molecule neutral, it is attached to 2 chlorine atom. And these species, this neutral molecule, we know that the chloride is also the labile ligands, so they can easily replace, they can easily replace by the methyl group, they can easily replace by any methylating agent, and we get zirconium eta 5 cp, eta 5 cp, one cs3 is there, one cs3 is there. So these chlorides are labile in nature, and therefore they can easily substituted by the methylating agent, and therefore these two chlorines are replaced by the cs3. Again, if you consider, let's consider the some derivatives of these zirconocenes. So let us discuss the derivatives of zirconocenes. So this is the difference. So what is before discussing the catalytic cycle for this alkene polymerization using metallocene, so we know that these hydrogens which is attached to these cyclopentadienes are acidic. It will loss H plus ions, so this cp ring loss H plus ions to gives negatively charged species which is aromatic. When it binds with metal ion, it will forms a sandwich component such as ferrocene. Sometimes the higher positively charged cation, it is also bind with this cyclopentadiene ring to form a neutral complex, that is, which is slightly differ in structure from this ferrocene. So let us discuss some derivatives of this zirconocene. So if we discuss the derivatives, so the first derivatives of this zirconocene, if you consider, this is your cs2 and this is attached to this cs3. So this is the derivative of bis chlorozirconocene to make the polymers, to make the polymers. So it is a derivative of bis chlorozirconocenes. So the chlorine atom, it is replaced by the methyl group, and the cyclopentadiene ligand, it is replaced by the ligands or the rings, that is, one is a 6-membered ring and another is 5-membered ring. The ligand, it is known as indinyl. So this is your indinyl ligand. Indonyl ligand. This is your indonyl ligand. So you should remember, whenever a 6-membered ring and 5-membered rings are attached to each other, then it is considered as a indonyl. So the CP ring, it is replaced by these indonyl ligands. And again, if you consider these indonyl ligands are these big bulky indonyl ligands pointed in opposite direction, and they are linked by the ethylene bridge. So if you consider this CH2 it is your ethylene bridge. It is your ethylene bridge. So these two indonyl ligands are joined by this they are joined by this ethylene bridge. So the big bulky indonyl ligands pointed in opposite direction. So if we see the structure, they are pointed in opposite direction as they guide the incoming monomers, so that they can only react when pointed in the right direction to give isotactic polymers. So in polymers, we are very much familiar with this isotactic, atactic, syntactic polymers. So once again you revise this, what is isotactic, atactic and syntactic polymers. So the main advantages of this metallocene base alkene polymerization is that we get isotactic polymers, means the polymers in which the stereochemistry is remains same, it does not change. And these ligands, that is the zirconium complex, zirconocene complex, it is used for this alkene polymerization. So if you consider this zirconium, it is the chlorine atom, it is replaced by the methyl group, and the cyclopentadienyl ligand, it is replaced by the indonyl ligand, and these two indonyl ligands are bridged by the ethylene molecules, and therefore it is an ethylene bridge. And this species, it is used for alkene polymerization. This species, it is used for alkene polymerization. So if you consider the cycle for this alkene polymerization, then let us discuss the cycle for this alkene polymerization using this zirconocene metallocene. Zirconocene as a metallocene. So this is your Zr, this is your CS3, this is your CS3, and this is your eta 5. It is not eta 5, so let us consider it is as your indonyl. So this is your indonyl, one 6-membered and one 5-membered, and it is attached to this methylene bridge. So this is your indonyl. So let us consider the mechanism for this alkene polymerization. So what happened in the first step? So this methyl group, it is not very labile, but if it leaves the metal ion, then what happen, it will forms Zr, this CS3, 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 and having a positive charge, and this is your indonyl, which is attached to this methylene bridge, and second indonyl is there. So this is the first step after dissociation of one methyl group. So no doubt the methyl, it is not very labile species, but due to the dissociation of this methyl group, it will forms a positively charged species in which this zirconium, it will shows the agostic interaction with this alpha hydrogen. So it will shows the agostic interaction with this alpha hydrogen to maintain the stability. So this is the first step. In second step, this species, that is, if you consider here this species, it will forms it will coordinate with alkenes carbon carbon double bonds. That is, in second step, if you consider this as Zr, this is your H H H, this is your indenyl, again here indenyl is there, and here it is in +1 oxidation state, so it will binds with your carbon carbon double bonds. So in this case it is the propylene, one of the hydrogen, it is replaced by this methyl group. So what happened, there is a cyclic intermediate is formed. So when if you consider this alkene, it is electron rich, one of the carbon is electron rich and one of the carbon is electron deficient. So this methyl group, it is electron donating, therefore it is electron rich, so it will attack on this zirconium. At the same time, the bond between this zirconium and carbon is break, and it will attach to this, it will forms a new bond. So what is going on, when this will attack on this zirconium, the bond is break and it will forms bond with this carbon. So what you get, so the cyclic intermediate, the cyclic transition state is formed, and what do you get here, zirconium, here the indenyl, this is your indenyl, it is attached to this zirconium, and what do you get here, if you consider this is the carbon which is attached to HCH3, and the next carbon, it is your CH2, and for this and the carbon, that is, if you consider this is carbon number 1, this is carbon number 2, so the carbon number 1, it is attached to zirconium, and the carbon number 2, on which this methyl group is attached, so CH2, and here we get CH3. So we get this species when a single monomer when interact with this zirconocene, that is indenyl ligand base metallocene, when it interact with the propylene, it will forms a species. So again it is in +1 oxidation state, so when it will react with single monomer, it will forms this species. Again the process is continuous, again one of the molecule, because it has a vacant site, so another molecule of propylene, it is also binds with this zirconium. So let us consider this is your Zr, indenyl, and then it is in +1 oxidation state, here HCH3 is there, CH2, and CH3 is there. Again another molecule, that is C H H H and CH3, another molecules, again the same process is going on, it will forms bond with this and this will goes here. So what you get here, Zr, this is your indenyl, it is attached to this, and this is your carbon. Let us consider this. Again this is carbon number 1, carbon number 2, so this carbon number 1, it is attached to this metal atom, and one hydrogen and one CH3 is there, and again the carbon number 2, that is CH2, and for carbon number 2, how many carbon is attached, 1 2 3 carbon is attached, so this is 1, again here H, CH3 is there, CH2 is there, and CH3 is there. So we get this species. The process is continue. So if you consider this process is continue, that is H and CH3, H and CH3, it is it will from the same side, it will not change its stereochemistry. that is this HCS3 is always from the same side when the reaction is continue until the last product is formed. So this is called, if you consider, this is called isotactic polymers. So we get isotactic polymer, isotactic, that is the stereochemistry does not change. The stereochemistry of this methyl group is remains same, it is does not change, and therefore this is the advantage of this metallocene based alkene polymerization, that we get isotactic polymers. And the last step, that is uh, the termination step of this catalytic cycle, that is if you consider it having a beta hydrogen, that is abstraction of beta hydrogen for the termination. So if you consider the reaction, that is Zr, this is your indenyl, here indenyl is there, again here if you consider H CS3, this is your CS2, this is your CH CS3, and this is your CS2 CS3. And if you consider a termination step, then with respect to this Zr, this is your alpha, this is your beta hydrogen. So this is a beta hydride elimination to stop the reaction. So beta hydrogen is transfer and the bond is break. So what you get here, we get here Zr, this is your indenyl, Zr indenyl. Again if you consider, it is in +1 oxidation state, it is also in +1 oxidation state. So indenyl is there, and one of the hydrogen, it is shift, one of the hydrogen, it is shift, and what you get here, so again it is in +1 oxidation state, and we get here double bond H CS3, and this is your so the bond is break and hydrogen is shift. So this is your one of the hydrogen, and this is your CHCS3, and this is your CS2 CS3. So the last step, that is the termination step, is beta hydride elimination. So this is all about the metallocene base alkene polymerization. So in previous lecture we already discussed the Ziegler-Natta catalysis for alkene polymerization. So the main advantages of this metallocene based alkene polymerization is that we get a isotactic polymers, that is the stereochemistry of the polymer does not change. So it is the main advantage of this metallocene based alkene polymerization. So you should remember this example, that is zirconium metal atom is there, 2CS3 which is attached to this zirconium, and the indenyl ligand, that is one is 6 membered, another is one is 6 membered, another is 5 membered, that is indenyl. Then there is substitution of methylene having positively charged species, it will shows agostic interaction, and this species interact with your propylene molecule to give the polymer. And the last step is termination, that is by using beta hydride elimination. So this is regarding to the metallocene based alkene polymerization. In next lecture we will discuss the remaining points regarding to this chapter. Thank you.